I'm here to talk about testing in prod and when that can be a really awesome idea for your business. I'm Dan, I'm CTO at Heap. A tiny bit about my background. I joined as our first hire in July 2013. My first project was building the initial version of the data system that powers this product, like how all the data actually gets into it, how we make it all useful and scalable and all that stuff. Before that, I was an engineer at a company called Palantir, if any of you have heard of that. Before that, I studied math and CS at Stanford. I did a bunch of deep learning research. That was kind of my thing then. If you want to geek out about that after, come talk to me. This is me in my happy place. This is me in a different happy place, I guess. What we'll cover today, I'll give you a brief primer on what Heap is, just the minimum stuff that you need to understand to make the rest of the conversation make sense. Then I'll talk about testing in prod and how we do that and why that works so well for us and the situations in which that can work well for you. And then I'll give you some thoughts on how to generalize this approach and some pro tips if you want to pursue it yourself. And finally, I'll walk through an example of a totally different scenario that we've found in which you can apply the same basic idea, and it turns out to work quite well. So what is Heap? Heap solves the problem of creating data sets about your customers and making them useful. So Heap is a tool that you would use to capture everything that your users do on your website or in your app and make that useful and answer questions later, find insights, do analytics, power your business workflows, whatever. I think it's easier to understand what this is in contrast to traditional tools. In a traditional tool, let's say I have this website and it has a page on it and it has a video on that page, and I want to know how many people clicked that play button on that page so I can know if it's going up or down or answer some kind of business question. This is how you answer that question in every other tool. You're probably like vaguely familiar with this, at least in concept. You add an event. Every single tool works the same way except for Heap. There's a tracking API where you add an event listener to that button, and then you write this one line of tracking code, and you track that the user watched that video or something, and then you ship this code, and you get the data, you answer your question. So this turns out to be very limiting because your ability to iterate on your data set is really poor. Like every time you want to add something to your data set, like a new event or track a new thing or fix a problem with it or anything like that, you have to go get an engineer to change your tracking code and wait for the code to ship and wait for your users to upgrade, and data has to accumulate and all that stuff. It's like multi-week, multi-month cycle to iterate. What we found is that the most interesting stuff is usually 12 iteration steps deep when you're asking questions that you didn't even know to ask up front. So that iteration speed is key, and this workflow is really painful. So the Heap approach to this problem is to capture everything your users do up front and then let you analyze it later. So your use of Heap starts with installing a snippet like this, or there's an SDK in iOS, Android, React Native that you install in your product, and we will start capturing every click, every page view, every form submission, whatever in your tool. And then when you have a question, you can answer it. So the way you answer it is you do what's called defining an event. So instead of tracking something, you create a virtual event or you create a definition. It's all terms that mean the same basic thing. So this is an overlay of your website in Heap with where you can't, I don't know how well you can see, but if you mouse over that play button, you get a little thing on the right that tells you exactly what it thinks a play is. And you can, it'll pick out the distinctive CSS elements of that thing or some other key property that makes it the click play. Then you can give it a name where that shiny red arrow is, and you can click that define button. And then you have this watch OppLoans video event, and you can use it like an event in any other analytics tool. You can make graphs or do conversion funnels or cohort analysis, behavioral analysis, all the sorts of things you want to do. And then one thing that is not obvious from this screenshot demo is I defined this event today, but we have data going back retroactively to months before. So that's part of the power of this product, is that you can add something and then have data going back years instantaneously to answer your question. So this is powerful, but it's a hard product to build, and it's hard for a lot of reasons. Like for example, that snippet is very complex. The actual problem of capturing everything users do in an app or in a website is really complex, and there's a million edge cases and details and product details you need to get right to get that right. And then there's a whole bunch of other design questions that come from this. The stuff we're mostly going to talk about today is the data engineering problem of Heap and how that is hard and some things we've done to make that work well for us. So some core challenges to the data engineering challenge of Heap. The first is that there's just more data. We're capturing like 10x or 100x as much stuff that users do because we're capturing everything they do as opposed to just the stuff you've whitelisted. So the data set itself is just much larger, and we won't ever care about 95% of the things that are in it because they won't ever match any of those definitions. Most of the random clicks your users do are just noise. So the data set is much larger and has much worse signal to noise. So the data engineering problem is harder from that. And then another one that we'll talk about a lot today is that the variability in ways users use this product is enormous, and that makes any sort of system harder to build. Like the different kinds of analyses that people use this for and the different shapes of their data set by different customer, all of that variability is different ways your product could perform poorly. Like any higher variability problem is a harder engineering problem. So we'll talk a fair bit about that today, but that's a difficult part about this. Every analysis users do is unique and ad hoc, and sort of like boundless in ways it can differ. And finally, this is maybe a little bit subtle, but it's super important to us, is that the data set that you're using in Heap has this fundamental indirection in it. We're capturing raw stuff like clicks and page views and form submissions, but you're analyzing semantically meaningful events like watches of a video or something like that, and the mapping between those two is dynamic. And that's the power of this product, is that you can add a new thing there or change the definition at a given point in time, but that makes it harder to build this system in a performant way. As an example of the kind of thing that you can't do that you would otherwise do, any sort of system like this, a bog standard technique would be you want to partition your data by the type of the event. So you might want to have your checkouts in one section of disk, segregated from your signups or your orders in separate chunks of disk. So when you want to do an analysis of checkouts, you can just read a tightly bounded part of disk, and this is faster because it's all in one place and you're not reading any stuff that's extraneous, and it's also a contiguous scan, which gives you better locality. It's faster than doing a bunch of point reads. This is like a totally standard technique. You can't really do this in Heap, or it's certainly much harder to do because what is and isn't a checkout can change at any given point in time. You can update that definition, your analyses have to update retroactively, or you can like add a new thing and you'd have to reorganize the whole disk accordingly. So like, this is just an example. The point of this isn't we can't do partitioning, that's a bummer. The point of this is like, a lot of techniques don't work, so it's a hard data engineering problem. Like the basic, if you were to boil down like data system performance engineering to like one incredibly reductive idea, it might be something like organize your data so as to make your workload performant. And fundamentally, we can't do that as well because the workload is in terms of this like layer of quicksand that we can't control. So it's a hard data engineering problem. So how do you make this thing fast? And just to be clear, when I talk about making this thing fast, what I like, this isn't a vanity thing. Like users hate looking at a thing that has a 30-second spinning thing, but like maybe they'll deal if it means they can get data they wouldn't get elsewhere. The reason this is a really killer problem for our business is that it determines who can and can't use the product. Like if we make this product 2x faster, that means that customers who are 2x larger can use the thing at the same performance. So that's the real thing for our business, is that the addressable market is bounded by how fast we can make the analyses here. So it's a super key problem for us. And we talk about making this faster. There's a couple like ground rules that I'll try to establish, or like goals for the process of making this faster. When you're starting out, you can just do like DBA whack-a-mole stuff where you read your slow query log, you find a slow query, you add an index or something, make it fast, like repeat that until you've like covered most of the known problems. That'll work fine. At some point, you'll exhaust all the easy stuff, the low-hanging fruit, or your usage will be large. Like we have hundreds of thousands of queries per week, and thousands of them are things we want to make faster. So like that kind of thing isn't going to work. You need to be able to make large, systemic, big chunk improvements. Like overall, the P95 moved this percentage per quarter. We're not going to be able to do that whack-a-mole style anymore. And another goal for us is that we want to be able to do this in a predictable way. We want to be able to get like a turning the crank performance improvement reliably every month, every quarter, or something like that. I think quite often performance engineering is treated like this like big adventure of discovery, and like we'll deliver a 10x win when we get it, or like it's a big fishing expedition or something like that. We wanted this to be a predictable, reliable thing that we could do with people who weren't like God's gift to Linux tuning or something like that. With like regular engineers could reliably produce wins here. And finally, this is the data layer of a data product, so our tolerance for bugs is really low. Like our tolerance for any kind of data loss or serious performance regressions or any sort of incorrectness in the results, like it's a super risky area of the stack where we have basically no tolerance for problems. So another way to think about this is we want to build a factory for making performance improvements. And this is basically the system we've come up for doing this. Here's a quick case study in like what used to happen, or like what has happened before. We wanted to roll out ZFS. ZFS is a shiny new file system. New for a file system means like it's 15 years old. We wanted ZFS because it has file system level compression, and our data set is huge and super compressible. And if the file system compresses it for you, you can have like half the disk or even less than that, and that's a huge cost savings that we could pass on to our customers or keep for ourselves. And it's no code change to our product because it's in the file system, so it's a super attractive thing for us. But it's also something we knew was risky, so we did a bunch of research and we built a custom benchmarking suite for this. and we evaluated our product extensively on all the angles that we knew that it was risky. Like we right profiled it, and we got what we thought was a representative set of read analysis queries, and we tested those, and we tested some maintenance operations and database vacuums and blah, blah, blah. We tested all the things we could think of up front to test. Everything was green. We were super excited. We decided to roll the thing out. This is a picture I took of what happened next. It was like a huge train wreck of a thing. I think like, I don't know, it was an enormous stubbed toe for the business. We started rolling it out. It took more than a month to roll the thing out because we have like a petabyte scale data set. This isn't something we can just do overnight. It takes a long time to do these. And everything was fine for weeks. And then weeks into the rollout, we started to see serious problems, which is a bad time to see those because you're already weeks into the thing and you can't just turn it off. And the basic problem we had was that we couldn't ingest the incoming data fast enough, which is a pretty fundamental problem. It means like data is queuing up, not getting into our system. We're accruing latency. So like we had an analysis. We were able to cordon this off to a small number of customers, but for those customers, they were looking at a thing that was like, hey, we don't have data from your product for the last month, sorry, which is a completely broken, like we just had to refund them. It's a completely broken, unusable experience. So we couldn't ingest data fast enough. It's a broken product. And resolving this took weeks. It's like the worst case where you're like weeks in and you're like kind of in too deep to go back, or going back is going to take weeks, and it's like fixing a plane in flight that's already on fire. It's like not a good time. This is a bad part of my life. So super bad, but kind of tellingly, this wasn't some YOLO like expedition that we did. This was something that we really thoroughly vetted. We had one of our best engineers safety evaluate this for like a month beforehand. We did a bunch of research. This is the most thoroughly at the time that we had ever vetted a change to our analysis layer, and it was an enormous like problem, mistake, self-inflicted problem for the business. So we tried really hard to vet this thing, didn't work at all. And if you're curious about like specifically what went wrong, the benchmarking had some holes that in retrospect, now that we knew how it didn't work, were kind of easy to see, but at the time I think were pretty non-obvious. One in particular was that we were testing with disks that were less full than in Prot, and ZFS has nonlinearities around write performance given the fullness of disk. Another one was that the benchmark was a scaled down version of the data set on a scaled down machine, but scaling up the data set and the machine, there was like a nonlinearity there. It doesn't work the way you would think it would. Those are both like reasonable things to do in a benchmark. I think kind of the point of this is that like if you try to foresee any possible way that your thing could have a problem, I think that's kind of like an endless fool's errand of a thing. And this also wasn't the first time we had something where the benchmarking didn't agree with prod. We'd had other changes where the benchmarking results were that something was going to be a spectacular win, and then we rolled it out to prod, and there's like no appreciable change, or it's kind of a dud or something like that. So we need a new system to do this. And I think the moral of the story is that any way your testing is different from prod is surface area for surprises when you get to prod. Like totally ideal world, you would fork the universe and play forward your change in the status quo 10 years and see which one has the better business value or something like that. Obviously you can't do that, but you can do some degradation of that, and any degradation of that is surface area for problem. So we thought, instead of starting from a benchmark and trying to bake in all of the possible ways that we can ever imagine this becoming a problem in prod, what if we just invented a safe way to get this thing into prod so we could expose ourselves to that variance and that entropy of prod sooner? Thus, shadow prod, which is kind of the system that we cooked up. It's actually fairly simple. Our software is built around a query cluster that has a master and some number of workers, and the workers do all the work of evaluating queries. We built a system that basically picks one of those workers and replicates the data set of it completely to another machine and replicates all incoming reads and writes to that machine to the second one, and allows us to measure exactly the performance that we would have gotten from the system. You can think of it like an A/B test for your database performance. So this thing is in prod in every meaningful sense. We just ignore the results from it. But in every other sense, this thing is baking in prod. Here's a picture version, same basic concept. So we have a cluster. There's data coming in from Kafka, and it gets fed to all these different worker nodes, which are then queried from a master node via the app. And all we're doing is adding an additional node to this that's a clone of one of the nodes that gets a replicated set of queries on the read path, and it gets all the incoming data on the write path. And we've written a little shim layer in our app where you'll run both variants of the things such that it hits both the different workers. This actually, I hope this isn't super complicated. I think the fact that it's simple is part of what makes it a good idea. So the process for evaluating a change is you spin up a machine that's the same as a prod machine, except it has your variant in it. Like in the prior case, it would have been that the dotted line machine has ZFS running on it instead of XFS, which is the file system we had before, and otherwise they're the same, and then you can evaluate exactly the problems you would have had. And we would have noticed that we couldn't ingest the incoming data fast enough before it was in prod. We would have been able to fix the thing. So we've been doing this for about 18 months, and we're at the point where evaluating a change to our data layer takes about 2 to 4 weeks of wall time, most of which is passive. Most of that time is hydrating the new machine or waiting for stuff to happen so that we can accumulate a data set of performance and then compare it. Like you want to capture at least a full week of data for us because there's intra-week variation in how people use the product and all that stuff. But like it's like 2 to 4 weeks of time, maybe like 1 to 3 weeks at most of engineering time, depending on the complexity of the change. And we've been able to improve the performance of this product by like 20 to 40% per quarter reliably. And that compounds. That's awesome. That's like over the last 18 months, we've improved this thing by about 11x, which is a lot for, especially because there's no like large rewrite that we ever did. It was just like clockwork. Every quarter it gets 30% faster, and then that compounds over 6 quarters to a really huge win. So being able to do that reliably and have like consistent, smooth improvement predictably. And we were doing this with a database team of 2 people, one of whom was a new grad out of college, and the other of whom was like a 21-year-old who joined the company when he was 18. So I think that's like particularly cool that we've been able to pull this off with a really small team of people who are like very smart, very hardworking, but not like, I don't know, the Michael Jordan of performance or something like that. It's like normal engineers are able to generate really good wins with this sort of methodology. Another thing that's very cool about it is that we can test all kinds of different changes. Here's just some examples. We can basically test any different layer of the stack. We've gotten wins at the hardware layer, the OS config, the file system config, the database schema, the indexing strategy on top of the database, the way the queries are run on top of that, like the vacuuming strategy, all kinds of different layers of the stack. You basically test anything that we'd want to do. The only things that you can't test with this approach are things that are basically rewrites of the system. Like anything that is an incremental change you can test, but if your proposed change is like rip out everything and replace it with HBase, like we obviously can't test that. But anything that's like a node level, a worker node level change, we can basically test. Some tests are harder to run than others, usually because it's harder to set up the machine a certain way than others. But like it's super flexible. We've been able to get like pretty impressive wins basically everywhere. And this is just a graph of basically the inverse of the performance. So we have at any given time we have a max customer size that we are able to serve, and every time we get a performance improvement, that goes up. We're able to serve a larger customer. So this is that over the last 18 months. It's like a smooth, steady improvement where every month or two the number ticks up, and we're able to serve a larger customer. That's a happy graph. The reason for the huge uptick in April is that we deployed 3 different like accumulated wins at once that needed a particularly complex rollout. Another thing that's kind of cool about this, just as like a backstory, is that that's a 2-person team that has a bunch of other stuff that they need to do. Like they build new analysis features and stability improvements and other stuff. And towards the end of last year, like October through beginning of this year, we actually took our foot off the gas from a performance point of view because we had outstripped the business's ability to sell. It was no longer a constraining thing for our business. So we've been able to pull this off with a team of 2 people that has other responsibilities also, and that this hasn't been their top priority the whole time. So this is happy. Like this is like exactly what we're looking for: predictable, reliable improvement. Like also in this time, we've had basically no degradations. We basically had nothing that we shipped that had problems. We had a lot of things that we caught in shadow prod as like subtle ways our product would be degraded by a thing that we wouldn't have caught. But we haven't had any like tire fire stuff. So generally, this works really well because it's super easy from a safety point of view to be confident that something is safe for prod because it's already in prod. Like there's really not a whole lot of way that this thing is running differently than prod when it's in your shadow prod thing. So it's like easy to be confident you can promote it. You're running exactly the same workload on it. If you're really worried about something, you can just run it for longer. But it's already in prod. You're just ignoring the results from it. And then added bonus is that you can set up, you can basically get a free test of your rollout process, which is often a complex thing too if you have a petabyte of data. But you can hydrate that shadow prod node the same way you would have rolled out the change, and you get a free smoke test of that whole process. Here are some pro tips if you're interested in building a system like this for yourself. First pro tip, I would strongly suggest that you do a whole bunch of AA tests to expose any kind of confounding variables in your setup. An AA test, you can think of this whole thing as an A/B test for your data layer. An AA test is just an A/B test where there's no variation. Like you set up a shadow prod node that's an exact clone of a prod node with no changes. And if there's a difference there in how they perform, there's something that you need to know about. Either that means you're setting it up in a weird way, or there's like an important variable that determines the performance of the thing that you're going to learn about, that you're going to figure out from this. Or at the very least, if you want to be confident that your results are good, you need to know that your baseline is not high variance. Like the variance between what you see in a baseline like null variation shadow prod node and the prod equivalent of that needs to be really small compared to the change introduced by your feature. Otherwise, like you're just measuring noise, or you're going to have to run your test forever, something like that. Another pro tip, the ability to align specific atoms in your experiment between your prod and your shadow prod is super key. By the specific atoms, I mean like the underlying things that you're trying to optimize. We have this set up, it may be easier if it's concrete. We have this set up such that the individual queries that go to each worker and the shadow prod equivalent, we can line up the actual queries. The specific mechanism for us is that like we jam a comment into the SQL that has like a SQL comment that has a hash in it, and we're getting the raw SQL on the other end, and we can parse it out and line them up. The specific mechanism is what's important. Like what matters is that we can line up the prod query and the shadow prod equivalent of that. So you're not comparing distributions of results, you're comparing query to query, and this is super key because it means you can do valuable subgroup analyses. Like if you aren't getting a win that you expected or something like that, you can like dig into why, or if you can find sub areas of your product that degrade even if the macro thing is positive. Like this turns out to be so foundational, so key that I would suggest designing your whole thing with this in mind. This is like a first order top of your decision tree trade-off that I would build around, just like because there's so many things that you can do with this that you otherwise can't do. Like another thing you could do, for example, is ensure that you're getting the same queries in both, that like exactly the queries that you have in node A or node B are the same. And like for us, that's queries. For you, that might be something unrelated, but the ability to line up the atoms as opposed to just the distributions is something I would suggest building around. Relatedly, we have gotten a lot of mileage out of building a sanity checker to make sure that the improvements that we're getting make sense. This is another great way to expose confounding variables in your experiment. For example, we're lining up all of like query for query, every query on the shadow prod node and every query on the prod node. And if a thing gets faster that shouldn't have gotten faster, we want to flag that because either it means that our change has an effect that we didn't know about, or that there's an important thing to learn about or we set up the experiment wrong, or there's something to learn about the world from this. For example, if we add an index, what I would expect, we basically have a set of allowed transformations from the prod version to the new version. So if I add an index as my experiment, and a reasonable transformation would be replacing a sequential scan with a scan that uses that index, or replacing a scan that hits a worse index with that index. But a transformation that does not make sense is like just a different set of scans. That doesn't, like, something is wrong there, or you need to at least learn something. And this is another really powerful way to flesh out weird confounding variables. For example, another thing that you might want to check if you're us is queries with the same query plan should not have different performance. If I have a query that uses my new index and I have a different plan, it should be faster, or it should be at least different. If I have two queries that have the exact same plan, but one of them is a lot faster, like something is, like the hardware is something is different here in my results, I should be suspect. I think the general theme here is like, be incredibly suspicious of your results at all times, and treat them with maximal scrutiny. Don't take like a comfortable, happy number on face value, because often it's not real. Like you'd rather find the variability here than when you roll the thing onto prod and don't get the benefits that you think you're going to get. So I'm going to generalize this a little bit, such that it sort of like explain the thinking behind this, and maybe some more abstract ways that this can be useful to you beyond just database stuff. Forgive the like enormous reductiveness of this thought experiment, but let's plot all of the ways that software can have a problem on a single axis, from super foreseeable to super unforeseeable. So a really foreseeable stuff would be like type errors. These are stuff that you can foresee usually pretty locally, for example. Like a type error is usually like one line of code where you reference a number as a string or a string as a number or something like that, and super local, super foreseeable. Or at that end of the spectrum, you'd have like business logic problems where you forgot to sort this result set and there's a problem in the thing from that. Like it's local, it's like local to a function or something like that. And then at the far other end of the spectrum, you'd have performance stuff. Like it's generally pretty unpredictable how something will perform. Like if you ask any data layer guru how fast HBase will be on my product, they'll say you just have to like benchmark your workload on it. There's no telling. It's just too complex. It's a system level thing, not a local level thing. Or beyond that, there's like environmental variability. Like if your thing is on-prem and it's going to be run in a million different configurations environments, like there's just so much variance that's introduced by that it's going to be hard for you to know all the problems up front. And then like the maximally unforeseen thing would be like entropy itself. Like Amazon has some weird network and machine failures happening at the same time and you break in a way you didn't expect. Or like a cosmic ray flips a bit on your platter and like your disk is like there's an infinite that goes all the way to forever in terms of like the universe is out to make your software break. So we have all these different ways software can break. Let's add the various interventions that we make to make software not break. There's usually like ways that these map along the same axis. And I think the things that catch foreseeable issues tend to be more local, and the things that catch systemic issues tend to be more systemic. So for example, at the far foreseeable end of the spectrum, you'd have like type checking catches your type bugs, or integration tests catch your integration bugs, or like static analysis will catch a whole bunch of different bugs in your code. Far other end of the spectrum, you have like load testing and benchmarking to assess your performance. Those are system level evaluations, not local level evaluations. Obviously, you can use those things for local pieces of code. Like the basic idea here is much more black box and systemic as opposed to white box and local. And then like the farthest other end of the spectrum is would be like chaos engineering, which is just introducing entropy of the world into your thing to break it before the world does it to you. So it's like making your software stronger by like adding as much entropy to it as possible. So like forgive that you could quibble with any of the details of where this is here. Like I hope the basic idea is not particularly controversial. So the reason that this works so well for us is that the problem of query perf at Heap is super high variability. We're working in a situation where like the number of different ways people use this, the number of different shapes of their data set is enormous, and trying to capture all that stuff in a benchmark is going to be like more uphill than just trying to introduce the chaos of the world to you. Just to give you some examples, like I sat down for literally 2 minutes and tried to think of things I know about how users use this product that are potentially of value to performance. And there's like an enormous laundry list of stuff. Like and a person will go in and will use the same events repeatedly because they're analyzing a shopping cart flow and they'll use the same events. So those are going to be cached a certain way. It's like super important to catch that in your benchmark. Or different customers have super different shapes of data where they have users that do a lot of events or users that do few events or different kinds of events or all that stuff. Or another really common workflow is someone will design will create a brand new event in that visualizer and immediately analyze it. Or you have intra-week variance, intra-month variance, blah, blah, blah. There's a million different specific things about how users use this product that are more complex than like take some queries that users run and run them and see if they're faster or slower. And then in the backdrop to all this is like a billion writes a day of new data coming in, thrashing all of your caches and determining what's in memory and maintenance operations and vacuuming and a weekly backup that hammers the disk. And like they're trying to even capture all of these things, like trying to even foresee all of these things is really hard. I've been working in this company for 6 years and there's a ton that I don't know, but trying to build a benchmarking suite that captures all of this is like a really complicated simulation project, and I still claim that you're bound to fail by not seeing some key variable of how your system is being used or what it's like in prod or something like that. So to express this idea in that graph, like the problem of performance engineering for us is much farther on the unforeseeable high variance system level side of the problem than at a typical company. And that's why this approach works so well for us. Like benchmarking is going to strain to move farther to the right in that spectrum, but this shadow prod approach of coming at it from the other side and like embracing the chaos and variability of prod and getting that into our code as soon as possible is going to end up working better. So if I were to boil this down into one simplified thought that you can take with you and be better engineering leaders, if you're in a context with a ton of variability, you might be better off looking for ways to test that against that variability safely in prod, as opposed to trying to encode all that variability and capture it in your benchmarks. Or if we're going to simplify this even more, to like a super simple mimetic thing. If you have a ton of variability, you should think, should I test this in prod, or is there a safe way to test this in prod, or test this in prod? And again, I don't mean like YOLO put it in prod. I mean, figure out a way to safely put this thing in front of customers so you can expose yourself to problems sooner as opposed to trying to know what all the problems are going to be. So here is a totally unrelated example that has come up in our product. Underlying our product is a JavaScript snippet that runs on your website and captures everything your users do. It's a super sensitive piece of code. It runs on like hundreds of millions of page loads a day. It's like basically like a piece of the internet at this point. And it's really, really sensitive because any bugs in there will lead to permanent damage to a customer's data set. Like bugs downstream of here, we can usually recover the data, but if this thing just isn't working, there's gonna be a hole in the customer's data set that's irreparable, and that's really unacceptable given the product that we sell. And if you get this wrong, you can break a customer's data set, or you can break a customer's website, which is even more unacceptable. Like you can break forms if you're not careful, you can break the customer's rendering or something like that, which is like something that people have absolutely zero tolerance for an analytics tool. So we totally can't have this thing. Super sensitive. And similarly, it's a problem with huge variation, like huge heterogeneity in how this thing is used. We've built a huge integration test suite across browser OS combinations and different websites, the ways people built websites and SVGs and using this library, that library, and loading Heap this way or that way, and all these different variations. We use Sauce Labs to spin up a ton of Selenium and like test all different ways we can think of. And you can play this game of like every time there's a problem, you add a new test and you prevent that thing from ever happening again. And you should do that. That's good software engineering practice, and we do that too. But you get to a certain point of maturity of the business or low enough tolerance for problems here. And at some point, you need to be catching these problems before they happen a first time. Like this is a key enough part of our product that we need to be able to ship changes to it in a way that isn't like terrifying every single time. So we need a better way to test this thing. Like the variability is just like trying to catalog all of the abuses of CSS and JavaScript that people have used to make websites before is like a thing you could do a PhD thesis on. So like trying to encode all of that, like there's no way you're gonna capture everything. At some point you need to just come at this problem from the other end of the spectrum and like expose yourself sooner to the problem. So we're taking a similar approach. We're building out what you could call a shadow heap.js. It's the same principle. We're trying to capture all the variability of the ways that this piece of software is used by getting it into the ways that it's used, by getting it in front of all the variability in a way that is safe and won't break websites and won't break data sets. So the basic approach here is we're cooking up a little thing where you can load two different versions of the Heap.js snippet on select customers' sites or a small portion of user base or something like that. And we can correspond the events that come through from each of them and see if the new variant is missing some events, or if we think that this new variant is supposed to capture an edge case that is actually coming through, or we can encase this whole thing in a whole bunch of like error catching and try catching and safety stuff, so sandboxing basically, so that we are particularly careful to not break customer sites with it, and we can like look for increased error rates, any sort of thing like that. It's the same idea. See if there's a way we can A/B test this thing in front of users. We have a way to line up the atoms and compare the results, and then we can just discard the data from the shadow heap.js thing at the end of it once we've made the evaluation that we want to make. One last quick thing. I always feel like it's weird at these kinds of things where a person talks at you about some work that their company has done, and like it gives you the impression that they did the work. I didn't write any of the code for this thing. I did not build this software. I'm just the person telling you about it. These are the engineers who actually built this thing. That's Jeff Anderson, Kent Ross, Michael Malice, Stanley, Enoch Chung, Gediminas Rapolavicius, and Andrew Dye. These are people who at some point or another have either worked extensively on building this system or used it to get big performance improvements and deliver a ton of value. And an exceptional bunch of humans who write really good software, if I do say so myself. If you are interested in working with people who, or if you're interested in having your picture on this slide or like working with them, blah, 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 come talk to me. So I think I have time for like 2 questions.
If one of those worker nodes that you have like writes data to a downstream system, how do you kind of isolate that so it doesn't write into like other production stores?
That's a really good question. Basically, we happen to have the abstractions in place such that it's easy to make that never happen, but you have to think through all of those things. Like, we have to make it such that the shadow stuff is never read from as an authoritative thing ever. And there's like a couple annoying special cases of that, but basically, like, there's a lot of really cool tricks. If you want to come to the office hours, you want to know, there's like a lot of really cool tricks in how we've implemented this such that it's safe and gives us the visibility that we want. But basically all that is specific to us, or at least specific to Citus, which is the data system that we use to scale out Postgres. But you'll have to figure out your own thing.
Hi, it was a very interesting talk. I have two questions. One is just about the position on performance engineering. It seems like, at this point, we're just used to horizontal scaling as a solution to performance. And people don't spend as much time looking at single node performance or finite cluster size performance, but you're investing a lot in that, as opposed to, let's say, taking an approach where you would say, let's just find a way to burst performance onto Lambda whenever the query is running too slow. So what's the kind of motivation behind the specific choice and the amount of effort you're putting into it? And a related question is, now that you've committed to performance engineering with such gusto, do you have a sense of the ideal performance your system can give you, so you know where to put in your effort or which module to optimize first ahead of the others, or when to stop investing effort into optimizing a module?
That's interesting. So I'll answer the second one first because I think it's a little less open-ended. The second question, if I understand correctly, is basically like, do you have a good sense of what the fundamental limits of this are, or how do you pick the investments? The thing that we realized before we started this was that we had no shortage of ideas. We had a huge list of ideas for ways we could make this faster. Like, it's a complex enough system with enough moving pieces that, like, if you work on the thing, you'll think of a million different like unexplored variables or ideas or something like that. So the point of this was just to build a system where we could try as many things as possible, and like the problem we had before was that testing one of those things took like months and also still didn't work well as a testing. So I guess I usually think of it as like kind of, this is a weird metaphor, but like kind of like the Saudi proven oil reserves thing. Like, there's always like 6 months of proven reserves of performance stuff that we can pull out of this thing, and then how much we want to invest in that is a question of the business priorities and stuff, and we can like tune that up or down, like try more things, run more experiments or not. The first question was around like horizontal and vertical scaling. Like, I certainly don't feel like we've like taken a weird stance or something. Like, we're definitely horizontally scaling this thing too. We can't use a lot of particular text. Like, we can't lambda scale this because getting the data, like the thing that we're optimizing here is the local nodes, because that's where all the time goes in the thing. So having more of those wouldn't necessarily help us per se. And in fact, we've had some interesting experiments where things where like chopping the data up into smaller pieces in ways that you might think would help have actually been counterproductive. One thing I didn't show in any of these slides is like all the things that we learned didn't work, because there's like, that's like equally valuable that a whole lot of stuff that we found like didn't work. But I feel like we're doing all of the above. Like, we do need to scale this thing horizontally, and also we need to make each node faster, because like we can't throw an infinite amount of money at this, and also I don't know, there's like multi-tenancy questions that like kind of determine the economics. I'll tell you about it after if you're curious about the details.
I have a quick question. Do you think that there is an extreme version of this where this is the main way people test a lot of different types of software in the future? Maybe in a continuous delivery pipeline, or for things that aren't so much infrastructure related?
That's an interesting question.
Maybe this is the first way you test your product, for example.
Yeah. Like, that was the dream with a benchmark. We were going to have a benchmark that was so good we could put it in the CI pipeline and give us a performance score. And even giving a single number performance score is like it's like a 50-dimensional performance problem. It's like, even that is something that we've like kind of failed to be able to do well. Doing this in CI, I don't know. I feel like doing the idea as like staging is kind of what we're doing here. It's like a step beyond CI. Like, Shadow Heap.js is like kind of staging for the Heap.js snippet, or Shadow Prot is kind of staging for the database. So I see it as more of an analog to like A/B testing that your product manager might do.